In this tutorial we are going to discuss about the very important concept in control system, that is mathematical modeling of control system, or it is also called as the analogous systems. We are going to find out the analogy between the mechanical and the electrical systems. So how the mechanical systems can be converted into electrical systems, that is our major concern here in this topic. Okay, so mainly the mechanical system, simple mechanical system, it is consisting of three main parts: mass, then it has the spring constant K, and the friction, that is B. So this is simple mechanical system. So first of all we need to find out the equilibrium equation of mechanical system. So force of this mechanical system is calculated by force by mass plus force by friction, force due to the spring constant. Force due to mass is mass into acceleration, force due to friction is friction into velocity, force by spring constant is spring into displacement. So we'll write all the things in form of displacement. Mass into acceleration is, in term of displacement, is d square x of t upon dt square. Velocity, it is dx of t upon dt, and it is already in term of displacement. So this is about the mechanical equilibrium equation in time domain, and in S domain it is m into d square by dt square replaced by s square, x of t becomes x of s, plus b into d by dt by replaced by s, x of t becomes x of s, plus k into x of s. This is mechanical equilibrium equation. Okay, now we are moving for the electrical system. Okay, let's first take the loop analysis. In the loop analysis we have voltage source, suppose we have RLC network. This is RLC circuit. Okay, the current is I of t. So applying KVL to this, we will get an equation for voltage, that is R into I of t plus L into di of t upon dt plus 1 by C integration I of t dt. Okay, so applying a Laplace transform to this, we are getting V of s equal to R into I of s plus L into s into I of s, d by dt replaced by s, I of t becomes I of s, plus 1 by C. For integration we are having one term in denominator, that is s, I of s upon s. So this is a V of s. So but here I of s is a common term, and this I of s, we know the current is rate of change of charge with respect to time. So I of s becomes, applying Laplace to this I of t, s into q of s. Putting this term in the above equation, we are getting V of s is equal to R into s into q of s plus L into s into q of s, means L s square q of s, plus 1 by C I of s becomes s into q of s, s get cancelled, so this is 1 by C into q of s. So this is the electrical equilibrium equation using force voltage analogy. So remember our equation of mechanical equilibrium equation. This is f of s is equal to m into, we have calculated this, m into s square into x of s plus, that is b into s into x of s plus k into x of s. And the v of s equation using force voltage analogy, in that particular order, it is L s square q of s. By rearranging the order, we will get L s square q of s plus r into s into q of s plus 1 by c into q of s. So here we can see here the analogy between the force and voltage, mass and inductance, friction and resistance, spring constant K and capacitance. So using force voltage analogy, we can say force is analogous to voltage, mass is analogous to inductance, friction B is analogous to resistance, and the spring constant K is analogous to capacitance. Similarly, if we go for the nodal analysis, means force current analogy, then in the nodal analysis, voltage is as a node, then resistor, inductor as well as capacitor is there, and we have current source. We have current source here. Okay, so here the resistor, inductor and capacitor, current for all. So current due to resistor, current due to inductor, current through capacitor, current through resistor is V of T upon R using Ohm's law, plus current due to inductor is 1 by L integration of V of T dt, plus current through capacitor is C into dV of T upon dt. Applying Laplace to this, we will get I of s equal to 1 by R into V of s plus 1 upon L V of s divided by s plus C into s into V of s. So here V of s is common for all. So this V of T, actually voltage is a rate of change of flux with respect to time. So the getting V of s from this, it is s into phi of s. We'll put this equation in the equation of I of s. So we'll get I of s equal to 1 upon R s into phi of s plus 1 by L. This s get cancelled, so it is only phi of s plus C into s square into phi of s. So rearranging the equation for the current in s domain, I of s is equal to, first highest degree term, C s square phi of s plus 1 by R s into phi of s plus last term is 1 by L into phi of s. Okay, so our mechanical equation is f of s equal to m into s square into x of s plus b into s into x of s plus k into x of s. So here we will see analogy between force and current. Force is analogous to current, mass is analogous to capacitance, friction B is analogous to reciprocal of resistance, and spring constant K is analogous to reciprocal of inductance. So the mechanical system can be converted into electrical systems using force voltage and force current analogy. So the three major terms, mass is analogous to the, in force voltage analogy, mass is analogous to inductance, friction is analogous to resistance, and the spring constant is analogous to reciprocal of capacitance. So mass is analogous to inductance, friction is analogous to resistance, and the spring constant is analogous to reciprocal of capacitance. And for the force current analogy, mass is analogous to capacitance, friction B is analogous to 1 upon resistance, and spring constant K is analogous to 1 upon inductance. So this is analogy for mechanical systems and electrical systems using force voltage analogy and force current analogy. Thank you very much.